Hello everybody, it's me again, Manji Ahmed. So today I'm going to be talking about hybridization of carbon. Now, first of all, let's look at what exactly is hybridization. From the word itself, hybrid, or as we know as a mix. So let's say for example in biology, hybrid is a genetic hybrid is an offspring that results from sexual reproduction of two parents that are distinct or different from each other. Like for example, the tiger. And if a tiger mates with a lion, their offspring will be called as the liger, or a mix between a tiger and a lion. Now, hybrid is a very simple concept to understand. Now let's talk about what the chemistry says about hybridization. Now, hybridization is a theoretical concept in valence bond theory that explains the geometry and bonding characteristics of molecules. It involves the mixing of atomic orbitals, specifically s and p orbitals in carbon's case. So since we're talking about hybridization of carbon, we will specifically talking about s and p orbitals. Now, before we move on, let's look back at our lesson about atomic orbitals. So, atomic orbitals, so in quantum mechanics, an atomic orbital is not a planetary path, but rather a mathematical function that describes the wave-like behavior of an electron in an atom. It defines a specific region and around the atom's nucleus where there is a highest probability of finding an electron. So basically, atomic orbital is the electron's address or the electron's house in that matter. As I was saying, it involves the mixing of atomic orbitals, specifically s and p orbitals in carbon's case, to form a new set of equivalent orbitals called hybrid orbitals. Now, we know that atomic orbitals are much more simpler. So, there are also hybrid orbitals. We will talk about that later on in this video. These new orbitals are essential for carbon's ability to form four stable bonds and create the complex structures characteristics of organic chemistry. So, hybrid orbitals are new orbitals that are essential for carbon's ability to form four stable bonds. So I will be showing a photo later on in this video of these four stable bonds create complex structure. So I will be showing the complex structure later on this video. Let's continue. Carbon's ground state electron configuration is 1s2, 2s2, 2p2, 2p2. In order to form four bonds, the carbon atom enters an excited state where one electron from 2s orbital is promoted to the empty 2p orbital. So, the carbon atom enters an excited state where one electron from the 2s orbital is promoted to the empty 2p orbital, yielding the configuration 1s2, 2s1, 2px or the variable x1, 2py the variable y1, 2p1 the variable z. Hybridization then occurs by combining these four half-filled orbitals in different ways, leading to the three primary types of bonding environments. So what are the four hybridization four half-filled orbitals? These are 2s1, 2px1, 2py1, and 2p71. Now that we know what uh, what is the orbital hybridization, let's look at the types of carbon hybridization. The type of hybridization is determined by the number of sigma, sigma specifically the smaller letter of sigma. Sigma bonds and lone pairs of the carbon atom forms in carbon-containing compounds. The number of hybrid orbitals formed equals the number of sigma bonds pulled plus the number of lone pairs on that atom. So first type is, here's the photo, sp3 hybridization or single bonds. sp3 hybridization, single bonds. Process. So the process are 1, 2s orbital mixes with all three 2p orbitals. 2px, 2py, and 2pz are mixed orbital mixes with 3. So it mixes to generate 4 equivalent sp3 hybrid orbitals. Now, the bonding. These 4 sp3 orbitals are used to form 4 single sigma bonds. Geometry and angle. To maximize the distance between 4 electron domains, the resulting molecular geometry is tetrahedral, or the shape that is making is tetrahedral, and the ideal bond angle is, take note, 109.5 degrees. So for example, in the photo, methane or CH4 and ethane C2H6, all carbons are alkanes are sp3 hybridized. Type 2 or B, sp2 hybridization double bonds. The process on this is 2s orbital mixes with 2 of the 2p orbitals. For examples are 2px and 2py to generate 3 equivalent 2s2p hybrid orbitals. 1p orbital 2pz remains unhybridized. So there is one orbital that is remaining unhybridized. So the bonding process is the 3 sp2 orbitals from 3 sigma bonds. The unhybridized 2p orbital is perpendicular to the sp2 plane and overlaps sideways with an adjacent unhybridized p orbital to form a pi bond, resulting in a double bond. Geometry and angle. The 3 sigma bonds define a trigonal planar geometry with an ideal angle of, take note, 120 degrees. So an example of this is ethane, which is carbon 2 and hydrogen 4 or C2H4, and carbon in carbonyl groups is C is equal to O. All carbons in alkanes are sp2 hybridized. So let's move on to the third topic, which is sp hybridization or triple bonds. So the process on doing this is 1,2s orbital mixes with 1,2p orbital. Examples are 2px. So 1 lang, isa. To generate 2 equivalent sp hybrid orbitals, 2p orbitals, 2py, and 2pz remain unhybridized. So the rest of the orbitals are remaining unhybridized. So the bonding process are the 2 sp orbitals from 2 sigma bonds. The 2 unhybridized p orbitals overlap sideways with the adjacent unhybridized p orbital to form 2 pi bonds, resulting in a triple bond. So, the geometry and angle, the two sigma bonds orient in opposite direction, resulting in a linear geometry and bond angle of 180 degrees. So an example of this is ethine, which is C2H2, and carbon in carbon dioxide, which is all we know as CO2. So in conclusion, hybridization is the key mechanism that determines the three-dimensional structure of organic molecules by changing the composition of its valence orbitals. Carbon can adapt to form stable single, double, or triple bonds. This versatility accounts for the vast array of compounds it forms. And that's all for the topic of hybridization of carbon. I am Nokman Ahmad. Thank you.